Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are completing diffraction part of this unit. We are doing the next topic of electromagnetic radiation, which is the diffraction gradients and the polarization. So these both topics are very the theory-based topics, and we have to know about the some things, some the last things about the diffraction, and then we conclude this topic. And in the next lesson, we will start with the next part, which is the last part of this unit. So let's start with the diffraction gradients. So what is diffraction gradients is like a term. So diffraction gradients is a sheet of a glass or a plastic which with the large number of parallel lines. When light is incident on the gradient, each line of slit acts as an individual light source. So it is a gradient, light or gradient. When we put an instant light on the gradient, they will move on to the different light sources, same like the interference we do in the Young's double slit experiment. So this both things are interconnected to each other now. So diffraction with a sheet of glass which has, when light pass to this, they will move on to the very large number of parallel lines which have the each slit have one individual light source on it and different colors they have. So this is a very the gradient where we can say that how much the light can be diffracted. So what is the advantage for the using a diffraction gradient? So there's advantage. The main one is that the bright fringes become very sharp and clear. When we pass the light in it and we have certain different colors on it, you can see that the bright fringes, the colors have the bright fringes, have very sharp and clear thing we have to see in the gradient when we see that, as you will have the more interference between the multiple resources. So whereas with the double slit experiment, the interference fringes were kind of fuzzy and not very sharp. In the double slit experiment, they are not very good to see. So diffraction gradient is like advancement in this double slit experiment that we can see the bright fringes and dark fringes very easily from that gradient. So that's the kind of the machine, or you can see that equipment in the lab that where we can find the how the light is sharp and how much they sharp and how much the distance they travel to the deflected. So that's all you have to do, and from here you can have one like a lab kind of question, and you have like question in this. So this whole question is talking about the small end approximation. We do run double slit experiment, and then we do the diffraction gradient with that two formulas in use in this. So determine the number of lines per centimeter uh, in the diffraction gradient if a third bright fringe is rotated 10 centimeter from the central maximum. When the screen is rotated 60 centimeter from the gradient, the wavelength of the monochromatic light is 500 nanometers. So they mentioned that we have to find the number of lines. So when the light is passing through the diffraction gradient, so they are the lines. So they are not like the particular amount of lights. They are like sometimes you get they depend on the light source we have. We have a sunlight, we have a white light. They depend on light that how many lines you get. So this all depends on. So we have that number of lines per centimeter we have to find. So if they mention that you have to find the number of lines per centimeter, if they given to you that, so this means you have 1 upon d, and in this you have to find the 1 upon d. So 1 upon d is the thing we have to find in lines per centimeter. So we have a third bright fringe, which means your n is given to you, n is 3, and they mentioned that this is located 10 centimeter from the central medium, so which means we have a x. So make sure your all things are in centimeters because we want lines per centimeter. So if there's anything in meters, you have to convert this. And the screen is 60 centimeter from the gradient. So gradient is a light source. So you have a 60 centimeter like L. So this you get. And the wavelength you have the 500 nanometers. One thing in that, to find the thing, because your this wavelength is in meters now. So when you use that thing, when you find the d, because you have to find the d first, again you can't convert it into 1 upon d. So when you try to find the d's, you have to be all things in meters because the wavelength is in meter and you can't like change wavelength very easily. So you can convert, for now you can convert all things into meters. So 10 centimeter in meters is 0.10 meters, 60 centimeter is 0.60 meters for to calculate the d. So first we have to check the angle as we do in the small angle approximation. So you have x, you have L, so you can use the tan theta, which is equal to x upon L. So tan minus 1, x you have 0.10 meters, L you have 0.60 meters. So when you do this, you get about 9.4623 degrees, which is less than 10 degrees. So you can use the small error approximation formula. You can use the small error approximation formula in this now. So what is the formula is wavelength is equal to hd upon nl. So you want to find the d. So d stays over there. You get this nl upon h. So wavelength is about 500 into 10 raised to power minus 7 meters. And you have a 3, and you have 0.60 meters, and that's you have 0.10 meters. When you solve this all thing, you will get about 9.124 into 10 raised to power minus 6 meters. Now you have to convert into centimeters again, because now your all calculations are completed. So divide it by, multiply this by 100 centimeter upon 1 meters. Meter cancel out. You get about d of 9.124 is over 10 raised to power minus 4 meters. Now you want 1 upon d. But when you like convert this d into like 1 upon d, you also have to convert this like 1 upon this. Oh, centimeter. So this thing also can be done like this. So now you have to just follow this step, and you can solve this. And so 1 upon d is equal to, you can solve this, you get 1.10 into 10 raised to power 3 lines per centimeters. So when that denote the per line, that only one line you have to find. If the mention that you have find a particular like lines are given to you, so you can like multiply at the end. But you don't write like that type of question, that not complex question. So that's your 1 upon d you have to find like this, with the all formulas you do with the in the young double experiment or small end approximation. That's all you have to do. So you get the answer. So differentiate one thing more. Now, like this is a further topic in this. So this is like a small topic that we have. So comparing and contrasting the visible spectra. We are also talking about the colors. So here we also have to talk about the colors too. So comparing and contrasting visible spectra produced by a diffraction gradient and a triangular prism is frequently on the diploma exam. So you get the question from the visible spectra, which we do in the spectrum, that the visible light will convert it into some colors, white light convert into colors. This also can be done in the diffraction gradient when the source of light, sunlight or white light can be there, so you can see the colors, bright fringes, dark fringes. So that's all you have to get ready about in diffraction too. So if you have a violent light which reflects the most, and then the other hand that red light reflects the least, and the red light if diffracts the most, so a violent light which deflects the least. So that thing you have to know in this, that which light reflects the most, which light diffracts the most, and least also. So if the violent light reflects the most, so red light reflects the least. Red light deflects the most, and the violent light deflects the least. So we have a mnemonic for this, that every dry lipstick requires a red lipstick, which will the violent deflects least and the red reflects least. So at the most, the red diffracts most, the violent refracts the most. So that's all. This is also small mnemonic. You get the question one question particular get from in your diploma. We'll do practice in the diploma questions when we do. So the small topic, the last topic we have the polymerization. The polymerization is a very easy topic, and this is like the end of the diffraction part. So one issue was evidence on the interference was not enough to distinguish whether the waves were transfer or the longitudinal. So the waves are longitudinal or the transfer waves. So you can know that transfers are of two types. These are the two types. So we don't know from the interference that what type of waves we have, transfer or the longitudinal. So after that, Maxwell predicted the waves were transfer in nature. So it was a time to try and verify whether they are true or false. So Maxwell can be like predict that the waves were the transfer waves. But then we have to know that this is true or false. So Maxwell performed one test. So the pair of polymerized filters were used. So you can use that, see over there that you have some filter. This is the vertical one and this is the horizontal one. And this is vertical one and this one. We call them the A first. Okay. The transfer waves pass through a vertical polymerizing filter, and which does not stop the wave. So this wave goes in, that transfer wave goes in, and it does not like stop the wave in the vertical polymerizing filter. But because this is the same plane as the wave, However, once the wave encounters the horizontal polarizer filter, the wave is blocked and nothing will absorb past the filter. So when it passed to the another horizontal, they didn't pass through this. You didn't see like something over there. So the transfer waves can be passed through the vertical polarizer, but it can't pass through the horizontal ones. On the other hand, if you have a longitudinal waves, so if you have a longitudinal waves able to pass through both the vertical and horizontal polarizing filter, as the longitudinal waves are not linearly polarized, so they are all not polarized along the direction of the travel. So if you do with the same thing with the longitudinal waves, you can see that they pass through the vertical one and also pass through horizontal one, and you get the something on the screen on the other side. So what's the prediction can be tell after that, that if you set up the two crossed at 90 degrees to the one another, if you put the things in 90-degree angle, when it filters in the path of the electromagnetic radiation, you will block all the electromagnetic radiation as it attempts to pass through a second filter. So that's the thing they do. You then crossed, like one you have the vertical one and when you have a horizontal one. So they pass to the electromagnetic radiation and you will block all the electromagnetic radiation in that one attempt, and it doesn't pass through it attempts to pass through the second filter too. So this shows that the electromagnetic radiation is a transfer wave, not a longitudinal wave. So that's the end of this, that electromagnetic radiation is now a transfer wave, not a longitudinal wave anymore. So you have to just know this thing in this now, that the electromagnetic radiation is the transfer wave. That's all you have to know in this now. So that's a last topic is not very important. You have just the one question from this and you have just to know about what are polymerization. So we turn with the part of diffraction 2. Now we're doing some practice portion of this part, and then we move on to the last part, which is the modern physics. Then we carry out this unit into the next unit. So that's all for this lesson. Learning with EduVibe, learn smart but not harder. Please like, share and subscribe to my channel. If you have any questions, let me in the comment section. See you in the next lesson. Till next week, I get with EduVibe.